Welcome everyone to the second lecture on the course Introduction to Artificial Intelligence. Before we go into today's topic, I went through the feedback I got from last time. There's this feedback activity in my courses, and many of you had gone there and posted feedback. Thank you for that. I think I had like 81 students who had provided feedback, and I was super happy about that. And many of the comments were like mostly thumbs up. I appreciate that as well. But then there were a couple of like suggestions, some of which are easily actionable, and others maybe harder. One of the actionable things actually concerns you who are here in this hall, because many of the students on the course watch the recordings. And then, well, I'm getting old. Sometimes I forget to repeat the questions. So whatever you say is not caught on tape. So if you have questions, we could circulate a mic. Or if you just want to shout out, that's also good. But then you need to make sure that I repeat the question. So then you just rudely interrupt me and say that you need to repeat the question. Do we have an agreement here? Yeah. So this is kind of a joint thing. You need to help me in order to help the others on the course. So kind of like it's a service to the community, so to say. Good. But if you have something longer that you want to ask, then just ask for the mic. It's easy to just, I'm just going to throw it to you, but then we can let you have it. Then there were some questions about will the course get more technical? Last time was sort of the really big picture, big and bold picture. It gets slightly more technical. But this is not a technical course. So then there are so many other courses that then make a deep dive into the actually how to implement the things, how to derive things. Like we have here on the blackboard we have equations, and well, those are for other courses. But it gets a bit more technical, and also then like a bit more specific in the way that we actually look into different models and methods. And some of them already today. Good. The audio was also not excellent in the video recording, and that's why we are trying this microphone today. Let's see how that plays out. Good. With that said, let's dive into machine learning. I tried to visualize data here on the first slide. And if we look at it, there is a multitude of different types of data. Of course, it's an image. It's actually generated by a machine learning model, which kind of makes it kind of like topical as well. But it kind of has these things representing audio, then these bar charts representing maybe some like statistical panel data or so on, and of course images. So today we dive into learning, machine learning, and typically data, not something to learn from, is important there. So the goals for today. Last time we looked into what AI is, and let's start by trying to see what machine learning actually is about. And it's maybe slightly easier to define machine learning than AI in general. And then I'll go through three central components of machine learning: models and methods, data, models, and algorithms. And then I try to conclude with examples of machine learning application areas. Any questions about today? And let's, like some of you were not here last time, we have this smart way of communicating with the lecturer. So if everything is okay and let's go forward, you nod. If things are bad, then you shake your head. And if I screw up, then kind of like face palming or so is also one way of sending a message. Good, okay. But do we agree on the agenda for today? Cool, okay, great. Last time we looked at AI, like the big, bold picture. And I've tried to project down the immense beast of AI into this two-dimensional blob here. So if this is AI, this blob here, we can kind of identify certain sub-areas within AI. And the lectures now, from lecture 2 until lecture 5, are kind of zooming into certain areas within this blob. And I need to warn you that this is my view on this. And as you remember, there is no generally agreed on definition on AI, and also then if we cannot define AI, also then saying that what belongs under AI and how to subdivide AI is a bit hard. So this is my view. So you can be critical, but you can also then kind of accept that, well, this is one way of looking into it. So yeah, so let's go with this. So some of the subparts that we looked into last time that we are going to zoom into on the course are here. So basically today we have a look at this sub-blob within AI. And as you see, we have things like data science, statistics, clearly overlapping with machine learning. That's just a positive thing. Okay, so we are zooming into AI, looking into learning-based methods. So last time we had an interest in can machines think? Can they be intelligent? We are maybe less broad this time. So this time in machine learning we replace the question can machines think with the question can machines do what we as thinking intelligent beings can do? And what can we do? What is that? Well, we can adapt to observations, we can learn from past experience, and we can understand visual cues and so on. Adapt, learn, understand. And these are kind of all things that if a human or say a robot or a general machine did any of these, we would typically assume that that requires some sort of thinking, intelligence, some mental processing needs to be done. So, intelligence often involves learning, being that artificial or not, and we can say that machine learning extracts higher level insights from data, from observations. And this means that one could say that machine learning is some sort of lower level AI, kind of some processing happening. Something goes in and something comes out. I like to think of a vending machine. You put in a coin and you do something and then there's an output. So there's some sort of processing happening, like an input-output. Or one could even say that machine learning is in some cases pragmatic AI. So we aren't actually interested in whether the machine is intelligent or not. We are interested in what it can do. So as a machine learner, I'm not really interested in making algorithms or machines that are self-aware. I think that I'm someone who makes tools, methods that are useful for people. And I don't care if that method is thinking of the sunset. I just want it to do what I teach it to do. So I'm maybe more practical in a sense, or more pragmatic. Does it make sense? Okay. So, one could say that like machine learning is concerned with computer programs or algorithms which use past data to learn how to make predictions about future data. So you have some data that you have observed and you want to teach a method to say something that would generalize to yet unseen future data. And this could mean that I train a machine learning method to recognize cats and dogs in pictures. And I have a training data set with cats and dogs, but then I want the method to generalize beyond the data that I show it. That would also recognize cats and dogs that were not in those pictures that were used during training. So I wanted to generalize. And in machine learning, the learning part is typically called training. You train a method. And of course now, well, we can draw some parallels to what is happening here in this hall. I'm telling you all this. And I provide you some input data. And you take that stream of this chaotic output that I provide as an input, and you try to extract the important parts of what I'm saying, doing here. So of course now the input that is streaming into your sensors, your eyes, ears, nose, I don't know if you can smell me, but I smell like flowers. So then you try to extract sort of the higher level central knowledge from that. That then you would generalize then to the future use cases where you need this knowledge. Typically, the learning or training happens at a separate stage. So you take a machine learning method, you feed in some data, you train it with the observations. And at some point, you use some criterion to decide that now it's fully trained. Now it's ready. And then you kind of ship it. Now it's going into use. Say you want to train that cat-dog detector. You take a lot of labeled images of cats and dogs, you train the method, and then you decide that now it's ready. And then it's put in use. And then it doesn't learn anymore. And this is fundamentally different from how you learn. If I tell you that now you're fully trained, now you stop learning. Can you do that? I don't think so. It's very hard to decide that I'm not taking any input and I stop learning. I would say that's practically impossible for us humans. But this is standard practice when we talk about machine learning methods. Of course, then there are methods that kind of do lifelong learning, so-called continual learning and so on, where the idea is that they would kind of adapt to data all the time and update themselves, the observations. But those are more kind of special cases and current things being researched. So typically, machine learning models are trained and then put into use. Great. Okay. Now let's dig slightly more deeper into how machine learning typically works. And this is machine learning here. This blob. And well, you can probably guess that if we talk about learning, we need some input. That's the data that is provided to the method. So the first ingredient in machine learning is data. We'll go into data in a bit. The second ingredient is a model. And the model kind of encapsulates what the person or entity building the machine learning method believes about the data generating process. This is where sort of like the prior assumptions about the phenomenon is encapsulated. We will go through certain families of typical machine learning models a bit later today. Okay, now we have something to learn from, which is the data, and a model that needs to be adapted to that data. But something is missing. We need the secret sauce that binds the data and models together. And that secret sauce I call algorithms. And this is maybe a bit harder to define, but algorithms capture all things that you need for training the model with the data and do future predictions about yet unseen data. So this is kind of like all the sauce that kind of like brings the other ingredients together. Also covering like ways of learning, which we will go into the second half of the lecture. Questions?
Can you explain again the models part?
The question is about the models. I have like, I think half of the slides are about models. But yeah, that is maybe like the hardest part, kind of like data is data. And I have slides about data as well. But I think we can all quickly grasp what data is. And if I tell you the algorithms is everything else, kind of, that's the source, secret sauce. But then the tricky part is the model. But I have several examples of that. So it's a good question. Let's dive into data. Should we? Yeah. So data comes first. And this is kind of like pretty clear, I would say, in a sense. So from a contemporary machine learning perspective, data is basically anything that can be stored on the computer. Data could be something else as well. I'm not sure how to store smells, but maybe you can sort of have a panel that would rank smells and so on. So I think even smells can be stored on the computer. But then images, audio, text, and so on, that's pretty clear. But just in case I have examples, just to show you that data covers a whole lot of things. So first of all, let's consider like traditional data. Data that maybe like comes to mind when I say spreadsheets or databases, like big tables with numbers. This is what people might think of when I speak about data. Yeah. Who thinks about tables with numbers when they hear data? 5 of you. Data can also be time evolving. Say it can be like access logs or event sequences or like bank transactions and so on. Of course, then like multimedia, like images, video, sound, music, and so on. That's also data. Text, like news articles, books, tweets, web searches, so on. You know what text is. Like we start from very basics, but you all know what text is. Location data, like coordinates, routes, how to go from one place to another, geotags, so on. This is also data. And of course, networks, social networks, road networks, like graphs of who calls whom with the phone, and so on. These are the networks, graphs. So data can come in many different forms. And there are machine learning methods to tackle like all these families of different types of data. I said that data is something that you can store on a computer. And of course, then we need to somehow represent the data as zeros and ones, like deep down, but basically as numbers. And if you have those big tables with numbers, that's pretty straightforward. You store the numbers in the memory and that's it. If you talk about text, this is very topical now with all the like generative AI models that use text. So typically, like text, there's a process called tokenization. And there's many ways of actually like encode or tokenize text. One simple way could be sort of this sort of like bag of words way, where you have some like corpus with words, and then you kind of put like a true false flag if the word is like there or not. So for example, here I have this corpus, this like list with I, you, am, are a cat, dog. And then I can kind of encode I am a cat into 1010110, just based on which of these letters are present in the string or sentence I provide. So using this logic, you are a dog, how would that be represented? 010101, exactly. But there are many ways of tokenizing or encoding text, and if we think of some big GPT model, it's a whole kind of research topic of its own, how to do efficient tokenization and so on. So doing it letter-based is not optimal, doing it word-based is not optimal, but something in between seems to work pretty well. How about images? And this is actually quite interesting, because kind of numerical data, like a table of data, or then text, that's kind of discrete. But then the word around us is actually continuous. Well, here's an image of a cat. For some reason I use a lot of cat images as examples in this lecture. So this is a cat. And to make it slightly easier to explain, let's reduce the resolution and turn it grayscale. So this is just like, I just made the pixels now bigger. Because the image is not actually continuously represented typically in memory. It's represented as a grid of dots or pixels. And then often, like you can have color images, but then let's consider this grayscale image. So basically, we have now it's a grid of grayscale values, or it could be color values, and we assign a number for each color, and then we basically store that as a big table of numbers. So now we are again in the realm of stuff that can be easily stored in the computer memory. This is a bit simplified, but this takes you pretty far. Data, there's certain things that you need to know about data, because I trust that you now kind of got that data is stuff that you can represent in the computer memory, and it can be anything that you can basically observe. The concept of labeled data comes up later on in the lecture as well. So labeled data simply means that each data point, being the point in a number, a location, or an image, comes with some additional information, a label. And the labels can go under various names. They can be tags, labels, classes, and so on. And for example here, the label represents whether there is a cat in the image or not. So for this image, the label is true. For this, it's also true. For this one, it's false. That's not a cat. And then for this, it's true, and for this, it's true. So there's some additional information associated with the data point. That's basically labeling. And this could also be seen as kind of like input-output pairs. Say I want to later on, when we go into ways of learning, I would like to train a model to recognize cats and dogs. So then it's good that I can provide this labeled set of observations to tell the model that these images have cats, you should look into these, and these images don't have cats, you should try to not misclassify these. The question was, what is meant by input-output pairs? We'll go into that in a bit. But basically, I can, for each of these, there's like, if I'm to train a model, then later on, to recognize cats, I can consider this image as an input, and this as an output. So when I train, I provide this labeled data set, and then when the model is trained, and we stop the learning part, and then put it into use. Then we would like the model to be able to take in these inputs and come up with a prediction for an output that is not provided when the data is fed into the trained model. Did this clarify? Okay, that was labeled data. What is unlabeled data? Well, this might come as a surprise, but that's data that doesn't have labels associated with the inputs. So this is basically kind of like just data without any additional information tagged to the inputs. And here are examples. This is like a big data set known as ImageNet. It's a big database with a lot of images. And now, like in the recent years, there's been like big data sets have been published with sort of like hundreds of millions of images. Why is this? Well, in order to train, for example, generative models that can generate images, they of course need to observe the world through training images. And that's why we need big data sets in order to train these big models. And of course, if we were to actually like label, provide information that what's in each of these images, that will require probably a lot of like human work to do the labeling. And labeling can be super costly. So typically these huge data sets come without labels because it wouldn't be feasible for someone to actually do the labeling. And that means that it's kind of easier to acquire like unlabeled data. You just kind of like go around and take pictures and save the pictures. But then if you were to write like tags that who's in the picture and what's in the picture and where the picture was taken, that would take up a lot of time. So unlabeled data is kind of like data without any additional information. Then there are like certain concepts that I'm just mentioning. Like one is data mining. And data mining refers to the process of discovering patterns in large data sets, kind of exploring. And this can involve methods from like machine learning, statistics, and also then like database systems. When you have enough data, just the sheer like management is challenging. Just storing, think that you have hundreds of millions of images. Just like storing and managing the data becomes a challenge. And I'm super happy, for example, that like smartphone manufacturers and so on, they have been like shipping tools also that use machine learning to auto-label and kind of help manage one's like photos. Because I don't know how many thousands of photos I have in my phone, but if it weren't for the kind of auto-labeling and stuff, I would probably never like find a photo that I know that I have a photo of some birthday party or whatever, but then like finding that, I would just have a huge pile of 10,000 photos would be very tricky. But then now I can search by like geolocation, by date, by keywords, by people and so on, which makes it easier to manage the data. One related term is also like knowledge discovery in databases, which like links to data mining. Data can be real meaning that there are actually things that have been like observed. Someone has like actually measured something with a tape measure, or taken real photographs of people or so on. But acquiring data at scale can be difficult, it can be dangerous in some cases, or it can be expensive. Think of like sending some probe to Mars to collect data. That costs a lot of money. And it can also in some cases be impossible. Think of some like medical data. It's highly unethical to kind of like make people sick just to observe what the disease would make or cause in the human. So we cannot do that. So then we might only have a handful of data samples, and it makes it hard then to do prediction or like modeling of the phenomenon. So sometimes it's actually like impossible. Or then it can be that the measurement process destroys the data sample. So that's why in some cases it can be good to use like synthetic data. That can also help make data more versatile. So think of, for example, training autonomous vehicles, like a self-driving car. And it's fairly easy nowadays to make like a good quality like simulator of like road traffic conditions under different weather conditions and so on. And then you simulate data and use that for training the AI. The same applies to certain types of generative models. So here I have some examples of them like simulated like traffic observations that you can then use for training. And this has been sort of like standard practice already for long in that field. I talked about generative models, and some of you might know, but OpenAI published a new model or product, depends how you think of it, that is kind of like similar to like say DALL-E or like these like generative image models, but it generates videos. And of course they are not disclosing how they train their model and so on. They have some details on how the model architecture works. But if you think of images, that's pretty easy to acquire good quality images. But when we talk about video, it's actually quite tricky. You can of course scrape the web for videos and so on. I know how, for example, if you would scrape YouTube for videos, what Google would say about that. But also then you need a lot more information than just images, because the phenomenon is not only like the photorealistic thing that you try to model, but you also try to model sort of then like consistency and like laws of physics and everything over time. So you would actually need a lot of data. And I don't think OpenAI has enough real data. So the easy way out and the kind of the sensible way out to train a model that can generate realistic videos is to use some sort of like physics simulator that can then like render videos for training. And I would believe that that's probably what they've done without actually knowing. And this is a generated video. That is certainly impressive. Pretty realistic, I would say. But a bit like video game kind of like. The motions are very smooth typically in these generated videos and so on, which might signal that there's some sort of like rendering engine that has been used for producing at least like a first batch of like basic training data that has then been fine-tuned with real data and images. So that's one example of where actually like simulating data can be very beneficial. Do you know what data is? Was that sort of like a comprehensive overview? Some of you are nodding. Should we go to models? I think that's the trickier part anyway. Yeah? Okay, models. And as I said, data, that's kind of what you observe. The model is where you, as the person building the AI or building the machine learning method, put in your expertise, your beliefs of what type of process or phenomenon is behind the data. What could be explaining the data or generating it, so to say. To show you a very, very simple model, and this is almost the simplest model I can come up with. So if the dots here are the data, and we consider some like labels here. So this is the inputs are on the x-axis, and the outputs, the labels, are on the y-axis. So then the data points can be represented by drawing them like this, as kind of input-output pairs. They have a x-coordinate and a vertical y-coordinate. Then I make a choice. I believe that a sensible way of explaining the data would be to say that the phenomenon is a linear relationship between, or an affine relationship between the inputs and the outputs. So I use my expertise here now. And I write down the model I believe would be behind the data in a mathematical form. Y equals A times X plus B. Question.
Can you figure out that the models part is more closely affected with like human decisions? Can you give these decisions to the algorithm?
The question is that can the models part be seen as being based on human decisions? I would say so, yes. Next time, in a week, we'll talk about deep learning. And there typically people try to explain this away by saying that let's use a very flexible model. A model that can adapt to almost anything, given enough data. And in that way, kind of like you try to say that you aren't making any strong assumptions because you don't know anything about the phenomenon. You provide a very flexible model and do learning in a data-driven way, that the kind of data will overwhelm any assumptions that will be there. This model is kind of the opposite here now. This is a very sort of like rigid model. This is like very strong assumption because kind of this linear model could not explain anything that could like, there would suddenly be a dot here. That would be an outlier, something that the model could never like believe that could be there. But this is a model. This is kind of like one of the simplest models that we could use in machine learning. And typically, machine learning models aren't as easily written down or represented as this. I use this as an example that you will see that at its core, there's nothing fancy about these models. They are typically some mathematical descriptions with parameters. And this particular model has two parameters. Parameter A and a parameter B. And these parameters take some values. They're just numbers. There is some value for A that makes the line fit the data, as well as for B. And now actually I can even sort of like read out what the parameters mean, which is kind of fancy when it comes to machine learning. The A is the slope, and the B tells about the intersection point with the y-axis. So I can actually sort of read out what is happening here in the model. And earlier I talked about learning or training. And to simplify, learning really means finding values for A and B so that they make the model fit the training data. So learning is basically just like searching for parameter values that explain the training data. And now in this simple example, it's quite explicit. You can even visually see when the line fits the training data. But then if we talk about then like next week about deep learning models, then you cannot really visualize these things. Then you kind of need to take that leap of faith and kind of hope for the best. And well, it really is just a model. And it's almost never in some real phenomenon is the model the right thing. It's a simplification. And George Box, who is a famous statistician, said once that all models are wrong, but some are useful. And in machine learning, this is very much the view. We are typically not concerned with whether the model is the right one. Often there is no right model, or the phenomenon is too complicated, or it changes over time, or so on. We want to choose a model family that is useful for the type of problem that we are tackling. And now if I go back to the previous slide, I generated the data, so I actually know what's behind this. And I can tell you that it's not a linear model. But the linear model here appears like a kind of like good enough simplification for it in some sense. Depends a bit on how much data we have and what the goals of the whole methods development or training here would be. So models are simplifications that typically actually some engineer building the machine learning method kind of makes the explicit choice that we'll use this model family because, well, typically it's maybe not that informed. It's more like this is my favorite family of models, or this is more efficient, so we save money by not using something more complicated or something else. So it's kind of like a decision that someone does. Probabilistic modeling. So related terms to this is like statistical inference, probabilistic methods, or like Bayesian approaches. And probabilistic modeling deals with quantities in terms of probability distributions. And the mindset here is the same, that the model kind of like has in it the prior beliefs about the phenomenon. And then in probabilistic methods, we try to make them like kind of update our beliefs based on the data in order to typically get some uncertainty quantification out from the problem. So we are not only interested in some prediction, but also in that how certain the model is about what it's predicting. And that's where like probabilistic methods come into machine learning. It's worth also then to mention this like basic kind of division about like regression and classification. So in regression, we are typically interested in estimating relationships between variables. That there's some relationship when I change the inputs, how do the outputs change? For example here, like this model here explaining that when I move this way along the input dimension, the output dimension moves this way. There's like a linear relationship between these two. So for example, say I would try to model that given how tall you are and how heavy you are, how old are you? And then I would collect a lot of data. I would ask this from everyone in the hall, and then I would make a model that would try to explain this relationship between height and weight and age. Classification typically tries to separate samples into classes, trying to like draw lines between inputs. Kind of like stuff on this side belongs to one class and stuff on this side belongs to some other class. That's easier said than done. especially if we talk about images. But classification applies to all types of data sets. So basically, I could formulate a model that, given how tall you are and how heavy you are, is your age over 25 years old. Kind of be like a binary classification model. Another concept that is good to keep in mind is also an interpolation versus extrapolation. Well, interpolation aims to fill gaps in between data points, kind of like, say, this part here. While extrapolation tries to kind of like go beyond the data boundaries, kind of like predict what happens here outside the observed data. And well, if you look at this figure here, that's kind of like quite explicit, what's in between data points and what's outside. But when we talk about, say, LLMs, large language models, it's a bit harder to say what is interpolation and what is extrapolation, or generative image models. So if I train a generative image model to generate new images based on text prompts, and I asked it to generate a photo of a cat dancing on Mars. So even if there are no pictures of cats dancing on Mars, it has seen in the training data images of Mars, it has seen cats, and it knows the concept of dancing because it has seen dancing in other photos. So then it can basically combine these concepts that it has learned about in order to create a new data point as an output that features a cat dancing on Mars. That's kind of interpolation. It kind of brings together these things, and even if there was no training data point with these things happening, it can kind of combine things. But then, if there's like a totally new concept that it should come up with, that's probably not going to work out that well. We are going into like different types of models in a bit. So often we also talk about then like how well you can actually like understand what happens inside the model. And one way of thinking of this is just like thinking of it like, well, black box models are models where the lights aren't on. You cannot really see how the cogs work inside the model. Something goes in, something comes out, but you can actually not like read out why the thing that came out. You have no visibility to what the model does. And that is very much related to the neural networks lecture next week. Then basically like kind of white box, or then like if you look at like gray box models where you can actually like read what is happening. You can actually read out that, well, okay, because that went in there, this part did that, and then this came out there. So they actually like, the parts can be very sort of like sensible, like human readable, what is happening. So in a white box model, we can actually understand what's happening. Should we have a short break? Let's continue. I talked about black box, white box models, how easy it's to like look into the model and understand what's happening. And that kind of relates to how easy to interpret the models. And that goes with something I call flexibility. And there's kind of a cost for flexibility, but also a need for it. So if we draw this graph where we have flexibility on the x-axis and interpretability on the y-axis, we can put our like linear regression model here. So it's not flexible at all, basically. It's very stiff. But you can actually read what the trained model is doing. Then we can have different families of machine learning models where decision trees are slightly more flexible, but there's a cost for that. Interpreting them is slightly harder. And then when we go through different typical families of machine learning models, you can read a trend here. And I'll have a slide of each of these model families next. But you see that the more flexible the model becomes, flexible meaning that it can actually adapt to more complicated data, the harder it is to read what it actually does. This is something that you should kind of like get out from this slide. Okay, so I'll quickly walk you through some of these families of these models. I'm not assuming that you kind of like master them in this one go, but this is just for you to understand that machine learning is not just like one model, one family of methods, but it's actually like a zoo of different kind of like animals, snakes and giraffes and elephants and so on, that are very different from each other, but all are valuable. Each of them have their own ecological box, kind of. They all serve a different purpose. And we definitely need linear regression models. But we also need neural networks. And if you remember something from models, remember that there are dozens, if not hundreds, of different model families in machine learning. And each of them typically have their like own dedicated purpose, what they are good for and why they are being used. But that is kind of like the discussions often overwhelmed with, say, neural networks or something that is used for things that are easy to explain. I use as an example classifying cats and dogs in images. Well, if I were to actually build a model for that, I would do that with a neural network. But that's only because I wanted to work with natural images. So neural network, it's like not so that that's like the go-to solution for everything. But there's typically a very hand-tailored, dedicated model that fits different purposes. Good. Decision trees. So this was kind of the next from linear regression. So it's a question.
Is it so that the models that you listed on the previous slide, some of them are more suitable to, let's say, only a particular type of data? For example, image is a two-dimensional data. So is it so that these models do not work equally efficiently for all kinds of data? Is it so?
The question is that, is it so that these models do not work equally efficient for like all types of data? And yeah, exactly. So the model is always a choice, kind of. You choose a model family that you work with. And typically that choice is an informed choice. You know that, well, I'm working with images. Then your expert knowledge says that, well, a neural network could be good here. Or you work with medical data. You want to do survival analyses with some like cancer patient data, or some medical treatment. Then you probably don't do that with neural networks. You choose something else. Or then, if you actually know that there is actually a linear relationship between inputs and outputs, and if you know that, then you choose a linear model, because that's knowledge that you want to put into the process. So it's very much depending on the problem or phenomenon that you are tackling. Good question. Any more questions?
When we are talking about data, actually, we implicitly need to talk about context, which data refers to. Because at the end, we are working with binary data, which are composed of ones and zeros. So we need to know the context of that. In which part of ML we are actually dealing with the context.
The question is related to that, where do we take into account the context of the data? Because then, if we are actually collecting the data, we probably have like broader knowledge of how, like, what it was collected from, what the background of everything is. So the context there. And that affects kind of like, that's the expert knowledge you have, kind of. You think that you know about the phenomenon or the data itself. So you take that into account in the modeling, but you can also take that into account in how you then like train the model or update the model based on new data samples and so on. So, but typically you would encapsulate the knowledge you have about the problem into the model part. Say you are a physicist and you know that you're measuring, say, measurements of the magnetic field. And then you know that, well, there are these laws of physics. Maxwell's equations tell you about magnetic fields. And it would be insane not to take that knowledge into account in the modeling. So then you would like to combine laws of physics, basically things coming from Maxwell's equations, with the model, so that the machine learning method would not first need to learn the laws of physics in order to make good predictions. So you try to encapsulate things you know typically in the model, but perhaps also then in how you train and update and infer things with the model. Good point. Decision trees. So decision trees are actually like a fairly simple form of machine learning. So basically, here you basically go down a tree, and then you typically make like binary decisions based on the values you have. And an easy way of thinking of this is thinking about like Titanic. You all know Titanic. Please nod. Anyone been on Titanic? Okay, so there's this data set of the passengers of Titanic. And we can train a decision tree on kind of the chance of survival based on the information that is present in the records of the passengers. So basically, the model sees as the kind of like first level decision is that whether the title of the person is Mr. This excludes Lord, Prince, all these fancier titles. So if the title was Mr., well, yeah, I have bad news for you. If the title is something else than Mr., then we can go into the next step here. Was it a third class passenger? If yes, in a big family, yes. I have even worse news for you. Third class passenger in a smaller family or traveling alone, a fair chance of surviving. Well, someone who is not traveling in third class and is not Mr. Is the title rare, like Prince? No? Well, very good chances surviving. Yes, not great chances of surviving. So this is a decision tree trained on the passenger data from the Titanic. Okay, that's a decision tree. Going like down the slope, k nearest neighbors. So here I have basically a classification problem. I have some inputs that are in this 2D space, and the class label is visualized by the color of the dot. And in k nearest like neighbor classification, any prediction point, let's say I would like to predict if I would have like a test point that would end up here. What would you think the label should be? What should it predict the label to be? Probably blue, I hear from the audience. I agree, because the closest points are blue. And then now like the decision boundaries would look like this. And this is super simple, kind of. You just look at the training data and then you predict by selecting the closest point and taking their label from there. This is quite understandable. And you can also do regression, so you kind of like then consider things to be continuous. Okay, still simple models. Okay, I talked about trees earlier, and you know what is a forest? Many trees. Yeah, a forest is many trees. Very good. So it's an ensemble method, constructing a multitude of decision trees. So basically, decision trees are prone to kind of overfit and so on, but then having several of those trees can like help with some of the problems. So this corrects some bad tendencies of decision trees. But of course, things become slightly more complicated because now you have several trees and so on. So yes, it's a bit of a hassle already. Support vector machines. And now we enter the realm of methods that start to be quite complicated already. So support vector machines are kind of like linear classifiers, but there also are these like nonlinear variants that kind of like wrap things up to like a sort of like higher dimensional feature space. And these are typically used for classification. So the idea is to find like planes, hyperplanes that cut through the data, in the input space and separate things out. Find kind of like ways to cut the input space so that kind of things are separated as much as possible. And I'm not going into details for SVMs, I'm just saying that even if neural networks are used a lot these days, SVMs still are kind of the state of the art, the best models for many classification problems. If you go outside like image classification, then typically you would probably not use an SVM. And then neural networks. And actually, we'll talk about neural networks for 2 hours next week. But I'm just saying that, well, there is kind of like a link or inspiration coming from how like the human brain or like biological actual neural networks work. And it's kind of like you could say that they are inspired by. And you have a collection of units that interact, and these models are extremely flexible, super hard to read what they actually do, but they can do a lot of like impressive things. And impressive things we will look into next week. So I'm not covering neural networks in more detail than that. Well, typically this flexibility of the model also means that there are more parameters. You remember the parameters in the linear model that we looked at. It was basically affine, there was like a slope and an intersection parameter. 2 parameters. That's simple. We think of neural networks then, extremely flexible. But then in order to fit to, say, image data or video data or audio data, you need a lot of parameters. And a lot of parameter means like billions of parameters, hundreds of billions of parameters, which is massive. And also actually understanding what a single parameter means is a bit tricky. So with more parameters also comes some challenges. And the challenges are related to underfitting and overfitting. Underfitting basically means that you have chosen a too simple model that cannot actually explain or adapt to the local differences or the local features in the data. While overfitting means that you have too few data samples to actually fit your very complicated model to. And I mentioned that you need these hundreds of millions of image input training samples to train these generative image models. And that is just because the model has so many parameters, it's so complicated. So in order to train it, you need a lot of data points. Okay, underfitting and overfitting. Basically, if this would be the data, would you choose a linear model for this? Could you explain this with a line? Nah. So you have a lot of data and you choose a too simple model. You underfit. The model cannot explain the data. Here, for example, you have very few data samples. And if I were to choose like a very high order polynomial and try to fit this to that, it could look like this. I actually fitted it to this data. And now the data is kind of like quite opportunistic. So this looks pretty linear to me. So if I would see this data and someone would ask me that, well, if I move this way, where would the next data point be? What would you predict? And I think you agree with me that it would go somewhere here. But when I fit this high order polynomial, it actually like overfits to these samples and then predicts that, well, it should go steeply down here. Which is, of course, we don't know. It might be that that's correct, but that's a bit weird, and I'm afraid that that's probably not the right model for this data set. So I overfit. I chose a too complicated model given the information that I have for training the method. If the same data used for training a model and testing it, there is an apparent risk to overfit to the training data. So you kind of like have like false confidence that your like trained model is working well. And typically how you train these models is that you take your data that you have at the training phase and you hold out. You don't use a part of the data in the actual training. And then you test with that data and see how well the model could predict that like left out part. And then you can shuffle this kind of called cross-validation, that you split the data into 5 parts, you hold out part number 1, train with 4 parts. And then you hold out part number 2 and train with the remaining 4 parts again. And then you shuffle through things like this. And that gives you maybe more knowledge of how it would generalize the data that you haven't yet seen. It is then shown to the data once it's being used then in the end use. That's called cross-validation. And especially with very flexible models, we should be very concerned about overfitting. It's very typical. Great. You asked about models in the beginning. Is it clearer now?
I'm wanting to hear about algorithms.
Should we move to algorithms? Should be. You're nodding at least. Yeah. Okay, so as I said, data, well, I think that's pretty clear now what data is. And I hope models start to also ring a bell. But algorithms, I call it the secret sauce, and it's everything else basically. So let's look into ways of learning. So an algorithm is an unambiguous specification how to solve a specific problem. It's kind of the recipe. So if let's say you're cooking, so the data is the ingredients, and then the saucepan you're using for cooking, and the oven, that's the model. So then the algorithm is the recipe, how to actually use the tools you have to bake the cake, so to say. I say a lot of things on these lectures. It's a secret sauce in the sense that it brings together kind of the other parts. So you could think of algorithms being a set of instructions or a description how to go through to train the model or evaluate predictions. But I also then consider algorithms in a very broad sense here for different ways of learning. And this is kind of central to machine learning, these different ways of learning. The first way is called supervised learning, and the second unsupervised. Supervised learning is basically training a model with labeled data. For example, I would have a collection of images here. I would show image number 1 and tell you that this is a dog. This is a cat. This is a dog. This is a cat. And I would kind of like inform you for every data sample what it is. And slowly you would learn that, well, dogs typically look like that, and cats typically look like that. So I supervise you by showing examples with known labels. Unsupervised learning is basically me showing unlabeled data. I would show you this photo, and this photo, and this photo, and you would need to figure out what is actually happening, what I tried to say. So, typically supervised learning is concerned with labeled data, with known inputs and outputs. And the goal is to train a model that could then take in inputs and predict outputs. It could do that for regression, to like describe relationship between inputs and outputs, or classification, like the dog-cat example I had. So the algorithm here builds or trains the model to capture the link between the inputs and outputs. It supervises the model. So then, like, given a labeled set of pictures of cats and dogs, learn to do binary classification of unseen cat-dog images. Or given your height measurements, or height measurements of a child up to age 10, predict how tall the child will be as an adult. Unsupervised learning is basically given samples of data without labels, unlabeled data. Okay, what's the point of this? Well, there is a point. So typically, unsupervised learning is used for discovering structure within data, understanding data, or also then learning to generate new samples of data. We looked at the Sora model earlier, or think of Stable Diffusion or DALL-E that can generate images. So you can train an image generator by just showing it a lot of images, and it learns the structure of images, natural images, in order to be able to produce new samples that are similar to the training samples. That's also unsupervised learning. So for example, given a large set of face images, just images of people's faces, learn what a human face is, or learn to generate similar images of human faces. Or, given a large set of hand-drawn digits, learn to tell them apart. So even if no one tells you that we have these digits from 0 to 9, so if you are given a big enough sample of hand-drawn digits, you can probably figure out that, well, these start to look similar, and these are similar, and these are similar, and you can cluster them into 10 clusters. Even if no one tells you that this thing is called a 1, this is a 3, and so on. Does it make sense? Cool. Then there's something called active learning, which is a special case of machine learning where the algorithm is able to query the user or some other entity for outputs of data points. So this could be seen as semi-supervised learning. I mentioned that it's kind of costly to label data points. So in this sense, the method could actually say that, well, now I need help. Can you tell me what this is? But then if it already knows that, well, this is a dog, then it doesn't need to ask that. So this is kind of an interactive process where the human provides supervision when it's needed. This could be pedestrian detection or customer feedback analysis. So if there's a weird feedback, then the method might ask a human to actually provide labels. Was it positive, was it negative, or so on? Or was it just nonsense? Feature learning, that's also then like something that you might stumble upon. It's a form of unsupervised learning that tries to like discover like patterns of underlying features of data. And it can be used for like simplify complicated data into something that is more easily understandable or easier to like read what's happening. And typically that kind of means, for example, like dimensionality reduction. And by dimensionality reduction, I basically mean that let's take these handwritten digits. You see that there are like go from 0 to 9. There are several of them. They all look slightly different. These are actual handwritten digits. And then we can use like a method that tries to map these images that are kind of like high dimensional into a two-dimensional space. And now like these clusters are different digits. And now actually I'm a bit bad with colors, but you can tell that these are zeros, if I'm not mistaken, and these are sixes, and this kind of like structure, it can like separate these out into clusters. Because even if they are hand-drawn and all look slightly different, there are still similarities that can be caught from there. And now if you think of, yeah, you could just, of course, like, just look at these. But say you have some very complicated, huge table of data that you try to find some structure in, then actually sort of then like doing dimensionality reduction can be very good to make it kind of like human readable. Quickly like catch things just by seeing it projected into some space where it's just easier to separate things out. Then there is reinforcement learning. And we will have a lecture on this as well. So reinforcement learning is concerned with how algorithms ought to take actions to maximize some cumulative reward. And this definition is just horrible. I'm sure that no one here like understood what actually is going on. But it's maybe easier to understand RL, reinforcement learning, through typical use cases. Say you're training a robot to walk. It's very hard to like gather data for this like training the robot. You could of course film someone walking and say that do this, but that's very hard to like kind of like make that into a form that a robot could actually like benefit from that. But it's kind of easy to specify kind of the goals or say give feedback when the robot succeeded. Let's say the robot is learning to walk. So you can give it a reward if it managed to move forward. So reinforcement learning is very much concerned with like trial and error. So think of a baby learning to walk. First, like the baby like explores what it can do with its hands and limbs, and then after a lot of like error and trying, it figures out how to crawl, then to walk on all four, slowly to stand up, and then to walk. And it's all based on kind of feedback, probably from well other people, but also from the baby seeing when it or they succeeded in doing it. So it's kind of feedback is key there. But we will have a lecture on RL, this question.
Google DeepMind made a quite interesting experiment with two robots actually playing the game of football. However, they weren't told that they were going to play the game of football. They were just simply told in their programming that this is ball and there is goal, you need to score to that goal. And after countless of trials and errors, they figured out what is the best spot to hit that goal and to score that goal. And after a couple of days, they already knew how to play the game of football without actually being told this is football. Can we assume that this is reinforcement learning?
The comment from the audience was that Google DeepMind had this application where they had robots playing football without the robots actually being told that they should play football. So they figured out how to kick the ball and so on their own through trial and error. And yeah, and the question was, can we assume that this is RL? Yes, we can definitely assume that's RL, especially because RL is kind of the favorite topic of Google DeepMind. They do a lot of RL, and also this example here on the screen is actually from something that we are going to go through on the RL lecture that also comes from Google DeepMind. So definitely. But more about RL than on lecture 5. It's a good example. So I have some example application areas of machine learning. And well, I'm not going to go through these because it will probably be more sensible to try to find some area where machine learning is not used at all. And that could be quite tricky because machine learning is used pretty much everywhere, I could say. Much of the current craziness around AI is due to certain advances in machine learning that has scaled up and solved some things that were not possible before. What those things are, we'll dive into that next week. But that has also caused that there is a very much interest in machine learning, and it kind of makes sense because like machine learning is kind of, as I said in the beginning, like the pragmatic side of AI. It's very much concerned with tools and tooling. And then in many fields, you typically want to have tools that makes work easier, more efficient, less dangerous, or so on. So, and often that AI tooling comes from machine learning. I'm just mentioning some application areas because they are kind of interesting and not covered elsewhere in the course. Anomaly detection is often coupled with data mining and also known as outlier detection, kind of like finding rare or surprising things. So basically identifying observations that don't fit your like assumptions about what should happen. And I think a good example of this is like detecting like credit card fraud by finding transactions that do not fit the user profile. As an example, when I was a poor student, I participated on an excursion to Ukraine. And as a poor student, I went to buy a very cheap flight. And I found an extremely cheap flight on some suspicious internet page that was maybe in Ukrainian. I'm not sure what the language was. But it was cheap. So I bought the flights from there by feeding in my credit card number in a suspicious text box. Don't do this at home. And I was super happy to find that within a couple of minutes, my phone rang. And there was someone, like an actual person from my bank, who was super happy that now their system caught someone trying to use my credit card on some suspicious website. And we have blocked your card. And they were so disappointed when I told them that no, it was me. And I wanted the transaction to go through. Turns out, the suspicious website was totally legit, and I received something that counted as tickets in my email. Everything worked out. I've never been so afraid in a plane as back then, but I'm still here, and it was a great trip. It was a long time ago. And nowadays, probably there wouldn't be a human person actually calling you, but certainly credit card companies kind of train models and try to detect if something surprising happens. And I'm super happy they do. The same applies for like identification of medical problems. if basically something, you go to like a checkup and they like measure stuff, and if something doesn't like fit the picture, then there's like something's triggered that now some additional checks are needed. That's detecting anomalies. Sentiment analysis. It's also known as opinion mining or emotion AI. And this is kind of like a combination of various things, like natural language processing for analyzing text, or like computational linguistics, or like biometrics. So in sentiment analysis, the idea is typically to identify, extract, quantify, or study like the affective states and like some kind of like subjective information. And this has gotten a lot easier now with like these big language models. So for example, like analyzing like free-form customer reviews, like responses to treatments, patterns happening in social network posts and so on. It's a bit like your feedback. I scrolled through the feedback, read the feedback, but then actually to summarize, I just took all the text and then asked an LLM to summarize like the positives and negatives. And I think it did a decent job. It even picked out comments that just like one person had posted there. So that can be actually a good way of summarizing a lot of information. This doesn't mean that you shouldn't post feedback. There's a feedback activity also for this lecture, and I'm happy to receive the feedback, and I'm actually reading the replies as well.
I have a question.
Please.
Not regarding feedback, but your feedback. But does AI understand irony?
The question is whether AI can understand irony. Well, these large language models, we'll talk about large language models next time. So they have been trained to kind of understand text, to generate text. And a complicated enough model can certainly also like capture things like nuances, vague ideas, even jokes, and even irony in a sense. It doesn't mean that it actually is ironic, but it can capture the concept in the same way as sort of then like, as you can kind of define irony in a formal sense. So the short answer is yes. But then whether it actually experiences that in the same way as we humans do, no. Is that an okay answer?
Yeah, I would imagine it depends on the situation as well.
Yeah. Okay, I'm going to tell you a story. We are almost at the end. We only have like 10 minutes left. I'm going to tell you about computer vision. Computer vision is an old field that has kind of gone in tandem with machine learning and AI for a long time. But it was very much kind of like a more separate field for a long time. And if you think of what computer vision is concerned with, so if humans we use our eyes to actually like kind of like perceive the surroundings, kind of like to help us navigate the world, like so that I don't hit things when I walk around, basically, or then like understand things, interpret things, read other people and so on. And we see effortlessly. We don't really need to make an effort there, but we have like billions of neurons dedicated just to processing the visual information in our brain. And visual perception is needed for many everyday tasks. And for machines to actually also kind of like navigate and understand the world around us, computer vision is a central thing. But computer vision, as well as like audio and language modeling, has gone through an immense paradigm shift in the past 10-15 years. Because for long, in computer vision, the the field was concerned with tailoring different like visual features and using that kind of understanding how the human visual system worked and trying to replicate kind of that in machines. And the same applied for language. Like computer language kind of like modeling was based on kind of like making semantic rules, like structure of the language and encoding that into a computer program. But this all shifted some 10-15 years ago when we learned how to make these flexible neural network models that can actually be trained not by telling them the rules, like grammar rules from language or how the physiology behind the human eye works, but just by showing examples of text, examples of images, and then in a data-driven and flexible way, letting the model adapt to the data. And that actually worked so much better in practice than trying to write down things in like explicit closed form. So this changed these fields a lot. So just to like show you an example. So I started my work in like machine learning related things maybe a bit earlier than this already, but in the start when I kind of like was coding up the first like image like recognition and classification models, this was kind of the best we could do. And basically what I'm trying to show you here is that this is nonsense. I don't even know what this model is trying to recognize here. So, but this is how things worked. So this is not useful. We go fast forward 10 years, and this wasn't a problem at all anymore. This kind of like solved. With enough data, you can train a model that is even better than humans on average in recognizing things in images, like everyday items, classifying people and segmenting them out and so on. With a big enough model and enough training data, machines can do that better than average humans. And these examples show that, well, these are like big segmentation results, and actually coding something up that is able to do this, if you are a competent Python coder and know a bit about machine learning, that's maybe 20 minutes of work to get that up and running. So this is not, it's not like a thing anymore. And yeah, these work very well. And even like segmenting out things from videos and so on work well. Well, this is a big model, but even things can be done in real time. So this is me chilling in my office, a bit, not far from here, with my favorite coffee mug. And then actually having a lightweight camera running on an embedded computer that can like classify things 30 times a second. That's not a problem. This recognizes me as a person, that's nice, sees that I have a tie on, and recognizes my cup, and so on. So these things work pretty well, as long as there's enough training data. Okay, recap. What were the 3 ingredients of machine learning? I hear the right things. Data, models, and algorithms. Do you feel that you have a grasp of machine learning now? Okay. Next up, we are going to dive slightly deeper into things. There are some questions.
Maybe it would be interesting to just hear a bit more about why machine learning is not AI, or if I'm talking about like, why is it important when I'm talking about it that I'm saying it's machine learning, not AI? Because I think that's like kind of the problem in the general conversation. Like when I'm talking with a developer, they will definitely talk about machine learning. But like in the previous lecture, we were discussing this as AI. So is that just semantics, or does it have a really like a point?
The question is related to that, like, is machine learning AI? Is it AI, or is it not? And is it semantics, or is there actually something behind it? on this course, now on this course, machine learning is definitely AI. So I would see that machine learning is a subpart of AI, because there are AIs that are not learning based. And we'll go into that as well on the course. We have one lecture on symbolic methods, where we cover non-machine learning AIs. But much of the things that we consider AI in the news and so on these days are machine learning methods, which then are AI, but based on typically flexible models that have been adapted to large data sets. And someone told me like 2 weeks ago that, yeah, the real AI, this Gen AI, generative AI, that's the real AI, and that's the only AI. But I call that's just BS. That's nonsense. So machine learning is definitely AI. I would say that it's pragmatic AI, something that kind of is concerned more with making things that appear intelligent than actually are intelligent.
Then maybe I can just continue and ask, why do you think for a developer it's very important to have this difference? He doesn't want to call it AI, he really wants to call it machine learning.
So the question is that there's a developer who doesn't want to call what he's doing or they are doing AI, but wants to call it machine learning. Well, that's up to personal preference, I would say. And also, I'm a professor of machine learning, not AI. So also then like people call these things many things. And of course, I do machine learning research, and that's why I call my stuff machine learning. But also there's this stigma that we talked about last time, that people are wary of the term AI because it's a bit hard to define. There's a lot of like, it's maybe a bit overloaded with expectations and ideas. People think about Terminators and whatnot. So there are a lot of people who want to speak about machine learning when they talk about methods that fall under machine learning. And I respect that. Good. So next week, we are diving into a specific family of machine learning models. We dive into deep learning. A question in the back.
Short question here on slide that says that you have a small intersection where machine learning is just statistics. Is that intention? Slide number 3.
Slide number 3.
Yeah, first one you really define.
Let's try to go, can I go that much back? Let's see. This takes a while. Bear with me. Slide number 3. That's way back.
Yeah, the small intersection where machine learning is just statistics. Is that intention?
Short answer, yes. This is just to cover my back from some colleague that shows up at my door and has a very strong opinion. Then like I said that, yeah, actually I left that part there. So, because I'm sure that someone exists that feels like this way. So, short answer is that it's actually there on purpose. Question?
Yeah, so I found that distinction between data models and algorithms is quite difficult, but when we try to like establish the differences between algorithms and models, it's a bit harder. And is there a better way of like specifying them?
I would say that the model is something that has parameters. If you think like that, then it can help you. Not all models have parameters, also like non-parametric models. But the model is something where you put your prior assumptions about the data generating process. So it's kind of a conscious choice that you make based on what the phenomenon is that you're trying to model. The algorithm is more about how you combine the observations with the model you have. It's more like a recipe how to deal with the different parts.
Can you think about it that like the algorithms, like the code, that if this and then that, to do that and that?
But the model can also be, model is also written in code. So it's a slippery slope to define things through code. Okay, I think I need to let you go. There's a quiz that's going to open. You have until next lecture. Next lecture is on Friday. The second exercise session is on Tuesday. You have until Tuesday to hand in the answers to the first exercise. Great. See you on Tuesday.